Welcome back, Chemistry 30. So we'll continue on with the molecular geometry, looking at adding more domains onto that central atom. So here the tetrahedral electron domain. So we have a central atom and bonded to 4 areas, or non-bond or bond. It is the tetrahedral shape. So if all of those 4 domains are considered important, it's the tetrahedral shape. And if we take one atom away, of course, we get a trigonal pyramidal shape. Trigonal meaning 3, and yes, it's a pyramid shape. If we take away another one, we get a bent shape here. So those deal with 4 electron domains, some bonding, some non-bonding. So those are the 3 here: tetrahedral if they're all bonding, trigonal pyramid if one is a non-bond, and bent if 2 bonding and 2 non-bonding areas. Okay? When I have 5 electron domains, I'm going to have to look at something first here. So look at the shape here. There's kind of 2 areas to look at. There's kind of like an axle shape or an axial shape, just like a car axle joining 2 wheels together. It's a straight linear type shape. And then there's an equatorial shape. So you can see this would make an equilateral triangle. So we have 2 shapes that we need to consider when we go above 4 domains around that central atom. So an axial position and equatorial position. And of course, going with that, the area that we remove electrons from is that equatorial area there. Okay, so knowing that, we can jump into something that has 5 domains around the central atom. So, of course, if all of those are bonding, we have a trigonal bipyramid. So, trigonal, so we have a triangle shape in the middle, and bi means 2, and then pyramidal, so 2 pyramids with their bases attached together. Now, when atoms are removed, they're removed from that equatorial area there, and we have a seesaw shape here. Now, you may be wondering, well, how in the world is that a seesaw? Seesaw. If I take this and tip it over like this, so that axial area is like that, then I have this and this. Ah, look at that. It looks like, so this is out in front, this is behind. Yeah, I'll put some people on here and they have a seesaw. I'm not sure what that guy's doing, but you can kind of see it's a kind of a seesaw shape. Oh my gosh, say that quickly 3 times. Pulling another one off, that makes sense. It's a T shape. And then pulling off the last one, it's linear. So there's 4 distinct shapes there with 5 electron domains. Trigonal bipyramidal if they're all bonding. Seesaw if we have 1 removed. T-shape if we have 2 removed. And if I have 3 removed, it forms a linear shape. And moving on to the last one, octahedral. May seem weird to call it octahedral when there's 6 electron domains, but you'll see here in a second why it is so. So we have a square region here, and a face here, a face here, a face here, and a face here. So there's 4 faces, and then 4 faces multiplied by 2 give us that 8 for octahedral. Now in this particular structure, as I mentioned with the other one, when atoms are removed, they're removed from the equatorial position. On this one, they're removed from the axial position. So here we can see there's a square and a pyramid, square pyramidal, and then over here, remove another one, square, and it's flat, so it's square planar. So all the positions involved with this one, octahedral, square pyramidal, and square planar. All right. If we're looking at larger molecules than that, it makes more sense to talk about the geometry about a particular atom rather than as a whole, because molecules can get quite big. So steps to determine geometry: write the Lewis dot structure for the compound, determine the number of electron pairs surrounding the atoms. Remember that double and triple bonds act as a single group or a single domain. And then determine the geometric shape that maximizes the distance between electron groups. This is the geometry of the electron domains. Mentally allow the non-bonding electrons to become visible. They are still there and still repelling each other, but we don't see them. The molecular geometry is determined by the remaining arrangement around the central atom. If I go back to this page, you can see here that for larger molecules, Yes, we can look at certain areas. So there's 1, 2, 3, 4. So we have a tetrahedral shape there. Here we have a bent shape. Here we have a trigonal planar shape. So all these shapes kind of make up larger molecules. All right, you may be wondering, well, how in the world am I going to remember all this? And the thing is, I'm going to give you a reference sheet if you haven't received it already. So the electron groups, or we could say electron domains. So 2 domains around the central atom. We have linear, 180. So you can see this is just a summary of all that we've talked about. 3 electron groups, or 3 domains. If I have 0 lone pairs or non-bonding, so you can label that as non-bonding at the top if you have this sheet. We get that. And of course, this is the electron domain geometry. So if I consider all important, all of these ones that have 0 lone pairs, these are equivalent to electron domain. So you may want to just write that on there. Electron domain, 0. Electron domain, 0. Electron domain. So if all of the areas are considered important, we have octahedral, trigonal, bipyramidal, etc. And then, of course, as I move down here, removing one, I get the bent shape, etc. So all the scenarios with corresponding pictures are there, as well as the angles between. So we can always have that to refer back to. All right, so let's take a look at this question here, and then you'll be able to do the assignment. So practice kind of making the structures and then outlining, okay, what is the electron domain, what is the molecular domain, etc. So kind of adding on to what we have been doing already. All right, so it says here, determine the electron domain and molecular domain geometry of CO2 and H2O. So they're both AX2 type molecules. At first glance, they seem they should be identical, right? But we'll see that there is a difference. So let's see, let's do CO2 over here, and we'll do H2O over here. Now CO2 is one that we've done over and over again, it seems. So we have 1 carbon, 2 oxygens. Over here we have 2 hydrogens and 1 oxygen. So they seem very similar shape. But as we'll see, there's a little bit of a difference. Carbon is group 4, oxygen's group 6. So there we get 16 valence electrons. Whereas over here with water, hydrogen is 1, oxygen is 16. 2 plus 16, we get 18. Or sorry, I made a mistake there. Not 16, but 6. I'm thinking of molar masses here. 8 valence electrons. All right, so putting the CO2 together, we've done this before. C in the middle, the O's off to the side. And we know darn well what's going to happen here because we've done this one so many times. 6 minus 7, yes, -1 I'm going to get. Carbon is 4 valence electrons, but of course there's only 2 involved with this structure. So yes, we know that we're going to have to move electron pairs downwards here to make this the most stable structure. This oxygen, 1, 2, 3, 4, 5, 6. So I get 6 minus 6, which is 0. Same thing over here. And carbon is a valence of 4. It should have, and it has 1, 2, 3, 4. So we're good. All right, so looking back, so I have 2 electron domains around the carbon, right? I have 2 areas where I can find electrons. 1, 2. And if I look at that, when I have 2 electron groups or 2 domains, there's only one possibility here. The electron domain geometry is linear, and also the molecular geometry is linear as well. So I can say electron domain geometry is linear, and the molecular domain geometry is also linear. So that's what I get for CO2. H2O, let's take a look at that. So I have O and H. Okay, I can't, so I've used up 4 electrons so far. And you know I can't add any more around the H's because they are full already. So add them around here and here. 2, 4, 6, 8, and I think that's all I can do. Hydrogen has a valency of 1. Oxygen has a valency of 6 because it's in group 6. So if I take a look here, hydrogen is contributing 1 electron, so yeah, it's good, and so is this one. Oxygen, 1, 2, 3, 4, 5, 6. It's good too, so that is the structure. So as we can see here, around that oxygen, I have 1, 2, 3, 4 electron domains around that oxygen. So if I look here, 4 electron domains. So if all of those were considered important, it would be tetrahedral shape. So the electron domain geometry, if I consider non-bonding and bonding areas important and contributing to the shape, it would be tetrahedral. Electron domain geometry is tetrahedral. Okay. But if I'm looking at, the molecular domain geometry, so now I look at what it actually is, and what I have in reality here is that 2 are bonding and I have 2 non-bonding. So when I have 2 lone pairs or 2 non-bonding, that's going to be bent. That looks a lot like my shape. The only thing is here is I drew it kind of incorrectly because I drew it as if it was linear, right? But in reality, it's going to look more like this, a bent shape. Now, do you have to redraw it? No. As long as you state that you know what the geometry actually is, we know that it is going to be a bent shape. So that's more appropriately what it's going to look like. So it's going to be bent. So molecular geometry is going to be a bent shape. So even though electron domain, it has 4 domains, so by default, we know what the electron domain geometry is going to be for all these. It's the one that occurs. If we were to think of it as, oh, we don't have any non-bonding pairs, they're all important, what's the shape? And then looking up the molecular geometry, you look at what it actually is by looking at how many non-bonding pairs or lone pairs are there. All right? So you should be able to do the assignment now. There's quite a few questions involving drawing and stating the shapes, electron and molecular, and you should be good to go with that. All right, we'll see you again.